Ionic bonding involves the transfer of one or more valence electrons from one atom to another. Keep in mind we are only considering the valence electrons as they are the ones involved in chemical reactions. Also, the word transfer is actually a simplification. In reality, there is no complete transfer of electrons between atoms, as we will see a little bit later on. Why would there be this so-called transfer of electrons? Because they're after getting 8 valence electrons. This is the octet rule. It says atoms react in order to get 8 valence electrons. There are a couple of exceptions. These atoms follow the duet rule. Atoms like lithium. When lithium transfers an electron, it has an outer shell with 2 electrons. So that's the duet rule. But most atoms follow the octet rule. Metals lose electrons. This forms a cation. And then nonmetals, of course, gain electrons, forming an anion. Anion with the negative charge because they've gained electrons, which bring their negative charge, and cations have a positive charge as they have lost electrons, so in effect losing negative charge. As an example, the metal potassium has 1 valence electron. It loses that electron, and then it now has a valency of 8. It has 8 valence electrons. The nonmetal fluorine, on the other hand, has 7 valence electrons. So the electron from potassium could come down to fluorine and complete that valency up to 8. Fluorine would then have 8 valence electrons. Oppositely charged ions are attracted to each other. There is an electrostatic attraction between the two. So, from the previous example, when potassium lost its electron, it became the potassium ion. When fluorine gained that electron, it became the fluoride ion. Because potassium ion has a positive charge and fluoride has a minus, there is an electrostatic attraction between those two ions. This attractive force is what we call an ionic bond. However, the force of attraction between a single metallic atom and a single non-metallic atom is actually not enough to remove an electron from the metal. Because of this, ionic compounds do not exist as individual molecules. Instead, they exist as a 3D lattice, a three-dimensional lattice of many ions. So it's more this situation. If you consider the green to be a cation, positively charged ion, and the yellow to be an anion with negative charge, then this is more the situation we have. The lattice can extend millions of ions in every direction. So rather than a discrete molecule with 1 negative and 1 positive ion, we have many, many ions, millions and millions of them. If you consider any one ion within the lattice, let's take this one, that one ion is actually electrostatically attracted to many other ions. So this positive ion is attracted to this negative, and this one below, and this one above it, the one behind it, and the two out to the side. So there's actually lots of electrostatic forces of attraction holding the lattice together. If you consider the negative ion, this negative ion is attracted to this positive and this one, the one below, the one above, and the one out to the left. Again, lots and lots of electrostatic force of attraction holding the lattice together. The fact that ionic compounds are held together with these many, many electrostatic forces of attraction give rise to some general properties of ionic compounds. For instance, they tend to have high melting points and boiling points. This is due to those strong electrostatic forces between the ions. These forces need to be overcome to melt and then to eventually to boil off the compound. Ionic compounds also tend to be soluble in water. This is due to the attraction of the polar water molecules for the positive and negative ions. Ionic compounds conduct current when molten or in solution. This is because the ions are free to move about. But when the compounds are solid, the ions are locked in place and a current will not be conducted.
Well, that's the video done. If you liked it, brilliant. Hit the like button and leave me a comment too. Now you know what to do. Go hit that subscribe button. We'll see you next time.